We are live. Okay. I will also put it on Equinox and come. Write something in yellow.
All right.
Yeah, this is a nice color. looks
But
looks
the
the
thing is,
contrast is good.
when I make it into a PDF, it's gonna become all whitey. So
Really?
this is how the actual PDF looks. If I pick yellow, which is why I don't usually pick yellow.
Oh,
This
okay.
is how the actual colors look. This is black
Hmm.
and red. You've seen. This is blue. Blue
Yeah.
gets contrasted differently. So
But the black background and white text is that gives better contrast.
Yeah,
yep.
but in PDF it gets converted to white,
Yeah,
right?
yeah. See, this Cian
White
Carroll
is
gave a
black.
lecture, 24 series lecture, biggest ideas of the universe. So that technology,
Mm-hmm.
to see that, that is very interesting.
Sean Carroll, huh?
Yeah, yeah, Cian Carroll, just type
Yep.
biggest ideas of the universe. There are 24 series.
Hmm.
So it
So
is
it's a
just,
series
it's
of
starting
24
from the, it
videos.
is neither pop science nor high-end mathematics. So it covers everything. So he has, actually, if you go for the preposterous so you get everything. He's in Caltech. Uh, Cian Carroll, biggest ideas of the universe in YouTube, if you type. So you see the technology he is using for teaching this, that's too good. So that I'm a little conversant with that. And he was using this Apple product, I think.
Yeah. I just hope my PC doesn't hang.
Nice. Okay, we can start in maybe another minute. You're using earphones, no? Okay. Okay, so if in the
Yeah.
middle, if the Wi-Fi gets bad or something, then you turn off the video. Otherwise, let
Sure.
it be on.
But you'll have to let me know about that. Okay.
Yeah, yeah, yeah. Okay, we're all here. Just before we get started, how many of you have exams this week? Can you like raise your hand or something? Or like exams inside Equinox, duration. Okay, one, two, three, four, five,
Five so far. Six.
five, six. Okay. All right. Um, okay, we'll keep that in mind. So if you guys have any,
I think I'll be done by this week, so it's fine. It's not that much of a problem.
okay, yeah, if you have timing preferences or something, just leave it on the Equinox Lounge. I'll try to keep that in mind. Uh, but otherwise there will always be the recordings available, so you can go through them. And regarding
My
the project,
exams are in the last few days of this, precisely 7th and onwards. 7th onwards of October, I have my exams.
okay, that's okay. That's just the last 3 4 days. Then yeah, that's all right. That's what I was saying. If you're lagging behind either in the project or the lectures, there is an additional week after 11th of October. So that additional week you can make use of and ask any doubts or continue the project. So yeah, we'll give you that flexibility. All right, Vikrant, we can get started. As you all
All
know,
right.
Vikrant is one of the cohort leaders here. He's been with Nakshatra this year. He actually joined somewhere in March, April, I think, and
Yeah.
he was part of this Einstein Pi group. We have a group in Nakshatra called Einstein Pi, and we basically make open source contributions to a general relativity library. But Vikrant is a more of a theory guy, if you will. You can see that today. And yeah, so he's definitely has a thing for theory, and I think he's a great student, and he recently started his master's in St. Joseph's. So yeah, including me, all of us here, a lot to learn from you. So let's get started.
All right, thank you. So before we start off, I'd just like to inform you that there'll be two parts of this talk. So in part one, that will be all about introduction to cosmology, and it's going to be very, let's say, simple with like just a few things. So what we'll cover here is the basic introduction, of course. Then we'll look at redshifts and expansion of the universe, of course. And then we'll go into the Friedman equation, just the first one, and the matter density of the universe. That's basically it. I would be covering only that much in cosmology, and this is quite a lot. So, if you will, after that is after part one, we'll have break, and part two is gonna get slightly mathematical. And what we'll do here is we will do basic math required for general relativity. So that'll be basic math for GR. What we'll do here is coordinate transforms. It's all quite simple, so it's all right if you're not familiar with it. Then we'll do the Einstein summation convention. Just write it as sum convention. And then we will do something called the Kronecker delta. You need not worry about the fancy terms. It's all quite simple to understand. And then we'll look at vectors, a new method of looking at vectors. And finally, we'll just stop at metric tensor. Just an introduction. It will not be very serious sort of a thing. But yeah, these are the things that we'll be covering. So let's go ahead. And oh, by the way, feel free to unmute yourself anytime and ask any question that you would want to. So it's been almost 2 weeks of Equinox. I'm also a cohort leader, so I've seen what every team has been doing, and how much development all of us have had with respect to our knowledge of astrophysics. So we've seen that the universe consists of stars, galaxies, and intergalactic dust, matter, and sort of radiations, and all of those sort of things. But then we need to wonder about, when we're studying astrophysics, what we need to talk about, what we need to think about is what is the physical and kinematical nature of the universe. How does it work? What's the dynamics of the universe? And what was its past? What's its present? What's the future? And so on, right? So these are the questions that cosmology deals with. So in brief, cosmology is like the study of the cosmos, the dynamics of the entire universe. And what this basically involves is so let me just write that down. Cosmology answers vaguely, because you can never have we still do not have like a perfect theory for the universe. It answers about the dynamics of the universe, kinematics, if you will. that just deals with the shape of the universe, the size, the density, and stuff like that. And let's also consider the future of the universe. All right.
What
So what
exactly
this
is
involves is
kinematics, or whatever, however you
you can
pronounce it?
understand it. You can understand it to be the let's say motion of bodies in the universe and stuff like that. So you might have done Newtonian kinematics, where you had the equations of motion, like v equals u plus at, and s equals half ut plus half at square, and those equations. So all of that comes under kinematics. I hope that clears it.
How
All
different
So
is
right.
cosmology?
basically, it
So
is motion and related.
yeah, but on a universal scale. So it's not your regular Newtonian stuff. You will have to bring in some extra stuff, which we will discuss. Someone else was also
Yeah,
talking. I'm not
how
sure what you
different
get
is
that.
cosmology from astrophysics? Because astrophysics is basically physics of the bodies, right? So is
All right.
cosmology a
So
study?
yeah. So astro here, you can astro. Let's break the word astro and physics. So I'm hoping that all of you understand what physics is and what the origin of the word physics is, right? This comes from the Greek word physique, which means the study of nature. All right. Astro deals with all the celestial bodies alone. You do not deal with the entire system as a whole. So let's say that astrophysics deals with celestial bodies and your how do I put it? Let's say planets and their motions, orbits, and stuff like that. Okay, cosmology on the other hand takes all of that and also tries to determine what the future would be, right? So cosmology is basically something that takes into account the shape, the size, and then what else? The density, all of the universe in totality. You can say astro is like a subset of cosmology. Uh, we build up cosmology from the principles of astrophysics, which I'll not be dealing with here. But that's like the vague method of thinking about it. So cosmology is all about formulating a theory by knowing all these things and by predicting what can happen. So, which is why we do not yet have a perfect theory for the universe. And yeah, that's at least how I understood cosmology. That what I understand cosmology to be. But you're always free to uh, come up with your own definitions. And one example for that is how you define time, because uh, you know there's no one proper definition for time, but the way I understand how I define time is the interval between any two consecutive events. So similarly, you can define cosmology to be the study of the universe, or you can define it to be study of let's say the future of the entire thing, or something, any way that you want to define it to be. But I prefer cosmology to be a definition of or the study of the universe in terms of its shape, size, density, the phase, um, the current stage of the universe, and stuff like that. All right, so that's how I would like to introduce cosmology to you guys. uh,
I have a doubt. Then
yeah,
what
sure.
is the difference between cosmology and astronomy?
Astronomy is an observational science, most of it at least is. So you make observations, and then those observations are sort of the basis for cosmology. So any theory that we come up with in cosmology, we would want it to agree with the results that is astronomically observed using your devices like telescopes and other sort of telescopes. That's the difference between astronomy and cosmology.
Okay, thank you.
Yeah, sure. All right, let's move on. So now we will briefly look at redshift. All right. So the history of redshifts go back all the way to year 1912, when an astronomer V. M. Sipler, did I get the spelling right? Yeah. simpler. So he was doing observations of radial velocities, right? So observed. I hope my handwriting is clear enough. Radial velocities uh, of nebulae. That's that's what he was studying. And what he found is all of them, the velocities, these radial velocities, were of the order of 1800 kilometers per second. All right, now this, when you see, is like a very high velocity. And what he also observed that few were approaching us, like the entire thing, but maximum were sort of going away from us. And how did he deduce that they were going away? Is when you do spectroscopy, which is when you're studying the light that comes from these stars, and you study it here on Earth. Let's say that the star, let's say, yeah, we'll call a star here, emits some sort of a light, and you are here on Earth, and you let's say this is lambda, and here on Earth you observe it to be lambda dash. All right. Now what you would observe is for the same, these are always your spectral lines from different elements. So let's say this was from certain element, like let's say helium, right? For example, it's not always helium, I'm just taking an example here. So what you would observe here on Earth is that lambda dash would not be equal to lambda, even if it's the same element. Like let's say even if elements were same. All right. So this is what would
One
help.
one doubt before you
Yeah.
continue.
Go ahead.
So by that time, this should imply that by that time, light's properties as a wave were quite well accepted. Am I correct?
Yeah, you could say so. But let's not get into that. Wavelength is a thing that has been going since Newton's time, and it was accepted since then. So you need not worry about that at all. The fact of the corpuscular nature of light and the wave nature of light is something that we need not bother about here, because we're talking in terms of wavelength and not in terms of energy. So you need not worry about it. All right. Okay, let's move on. So what they figured out is there was this factor called Z, which was defined as delta lambda by lambda, or in other terms, lambda dash minus lambda over lambda. Where I should probably change the notation then. But this is lambda, and this is all right. So what this means is whatever the wavelength that they observed was different from what you would actually expect. So in other terms, to think about it, is if your expected lambda was, let's say, I remember sodium's, which is 5893 angstrom, or that just means 5893 into 10 to the minus 10 meters. This is the wavelength of sodium light, right? But you observe lambda dash to be like, let's say 5893.5 maybe angstrom, which just means that it is 5893.5 into 10 to the minus 10 meters. Now you see that there is a difference delta lambda of zero point 0.5 angstrom, right? So now this tells me that whatever I have observed has actually elongated. It's sort of stretched out, and the wavelength has therefore become more. So if you want to see it pictorially, fine. If you want to see it pictorially, you have, let's say, a wave like this. This is your regular wavelength, where your wavelength is defined like this. All right. So what happens during a redshift is, sorry about that. All right, so this is your wave. So what happens is, whatever, let's say this is supposed to be the original. So I'll write it as lambda original. What happens when you observe this redshift is it sort of becomes like this, sort of expands out. So you see there is a difference. So if you compare the peaks of those, which lie here, this is the delta lambda that we observed, which in our previous example was somewhere around zero point 0.5 angstrom. Now, what this tells us is since it has elongated, that just means that the space between the star and our observation, this space, let's say D, has sort of increased by the time this particular thing reached here, right? So that just sort of tells us that the universe sort of expanded because there's nothing in between. You're not assuming any dust or something and all of that. And this was figured out in 1929 by, we all know who, Edwin Hubble. All he did was he observed the velocities of these nebulae and other stars from other galaxies, and he figured out that this redshift is caused because of the expansion of the universe. So redshift implies universe is expanding. All right. And using this fact, he could calculate the velocities to the of the particular body that he was observing. So this z factor is called the redshift, which is defined like this. And this also is equal to v over c, where v is the velocity of, let's say, a galaxy or any body that you're observing. All right. So that will give us v equals delta lambda by lambda into c. So this would give us the velocity of that particular galaxy in terms of the speed of light. Now, he also concluded the famously known equation v equals h d, where d is the distance that we saw here, this very distance. All right. So, yeah, v equal to ht. Now, this is the very famous Hubble's law, which mathematically showed, this is not the entire proof, but which mathematically showed that the universe is expanding. And from this relation, you can deduce that the velocity v is proportional to the distance, which means if d is more, or if the object is farther, then the velocity is also more, which means it is faster. And this is how we conclude that the farther something is, the faster it is moving away from us. So if I had something at 10 centimeters moving at velocity v1, and if I had something at 20 centimeters moving at v2, then I can directly say from Hubble's law that v2 would be greater than v1, something like that. It's not in centimeter scale, but this is basically the whole idea of redshift and so on. Now from here we can find out another fact. All right, so let's.
Can you just explain the math again, but a bit more this brought down level?
Okay, fine. What exactly didn't you understand? Let me just go back to that
The whole
first.
math part itself here?
Okay, fine. So basically, what's happening here is the star emits some wavelength, some color of light, let's say, and by the time you read it here on Earth, the color has changed. All right. So, do you know about the electromagnetic spectrum? Or let me just.
Yeah, yeah. I know about the
You know the
electromagnet.
Vibgyor thing, right? So you know that
Yeah.
red has longer wavelength.
Yes.
All right. So let's assume that this star emits blue light. All right. So
Okay.
this star is emitting blue light, but by the
Hmm.
time you see it here on Earth, you see it became red.
Okay.
All right. So you measure that difference. You measure the difference between the lambda of blue light and the lambda of the red light.
Okay.
Okay, that is this delta lambda factor here. Delta lambda means
So
the difference between the two.
change
Yeah,
in
change
lambda
in the
by
wavelength.
lambda.
Yes. So in this
Okay.
case, it would be, let's say, delta red, lambda red minus lambda blue. I know it was supposed to be some particular value, so I'm just gonna put that as lambda blue because I know that it should have been, I should have observed blue, but then I'm observing red, right?
Hmm.
Is that
How do
clear?
you know the actual value that it's supposed to emit? Like, we
That
know the
comes from your
observed value because
astronomical
we observe it.
observations of of the spectroscopy thing. What you do, that's a little complicated process. Let me see if you can
Okay.
understand that. So what happens here is, you know what the element that you're supposed to see. So let's say, so this is how the spectroscopy thingy
It is
looks.
because of fitting, right? You just fit the two spectra and then you get, right?
Yeah, exactly. So if
What
this is
you
supposed to
were
be the
supposed
original
to get,
line,
but what you did get. You just fit them and
yeah,
then you get your this. Am I right?
yeah, absolutely. So if you can see this picture here, this line is supposed to be the original which I'm supposed to get for that particular element. How that comes is from your astronomical techniques. I'm not going to get into that. But whatever you observe is, let's say, here, right? So that you know that it was supposed to be here, but then you're actually finding the line over here. So there is the shift here. This is your change in the wavelength. And so this thing, if let's say this was lambda naught, this particular value here, so this I will just figure out what the ratios, how much it changes, how much it changes with respect to the original. And that would give me my so-called redshift value. Is that clear?
Yeah,
So
yeah,
basically, I have to divide this change by the original value I should expect
Exactly.
itself.
Exactly. It's like how you're finding out percentage of increase or percentage of decrease and so on. Your 11th standard, 10th standard maths.
yeah.
Is that clear now? Is anyone
Yes.
else having any other doubt?
Yeah, not at all, but different analogy.
Mm-hmm.
So the change in the wavelength and the frequency, can it be due to the travel time taken,
Yes, of course, you can,
change
but
in
you
energy?
always end up measuring wavelengths. Wavelengths are easier to measure than energy. You also have the relations, right? You have E equals hc over lambda, so you
Yeah,
can convert, or E equal to hf. So
and
it's
as it
fine, but
takes.
you end up measuring wavelengths always. So
Mhm.
it's sort of easier to measure wavelengths over frequency or energies. Once you figure out wavelengths, you can always find out the rest of the values. So it's fine. Anything that you want to observe. All right.
Mm.
So can I move on?
Yeah,
All right. Cool. So now we will look at another very important thing. We have v equal to hg, and we know that velocity is equal to distance over time. All right. This is something that all of us know from our very basic foundational fundamental physics, that velocity equals distance over time.
What
Now,
is
when you,
H exactly?
I'm coming to that. That's the exact thing I'm coming to. All right. So you know this from your fundamental physics, where velocity equals distance over time. And when you compare that with this equation here, you find that h, whatever that is found to be 1 over time. Now, the reason we have a h here and not something like time or something is because of Hubble. You have to thank him for that. This h is called Hubble's constant. Now, getting into the full details of Hubble constant will take up a lot of time. But in brief, it's just a constant that helps us determine the age of the universe. How and stuff. I mean, why does it define the age of the universe? Is, let's say, a little longer conversation. So perhaps I'll put that down in the notes when I send it to you guys. But as of now, all you need to know is this Hubble's constant helps us determine the age of the universe. How is because of this relation. So if you see, I hope all of you are familiar with your regular dimensional analysis. So if you see here, Hubble, the dimensions of Hubble's constant is that of T inverse, or in other terms, seconds inverse, 1 over second. So if I just, invert this, I get time is equal to 1 over the Hubble's constant. Now, the value of Hubble's constant is somewhat a debated value, and it depends purely on your observations of the velocities of different galaxies and when you calculate their distances using this very law. So what you get generally is you have a graph that you make out of your regular observations, astronomical observations here. And what you expect is you expect to get a straight line where, where you have the distance d here, and the velocity here, because this is of the form y equals mx. All right, that's your regular line equation, straight line equation passing through the origin. So what happens is when you make observations, you will find that the velocities and distances of the different galaxies that you measure lie more or less on the same line. So you can sort of, get a rough observation. And when you find the slope of this, slope is equal to V over D, that will give you the value of Hubble's constant. The value of Hubble's constant depends on how accurate your measurements are to these galaxies. This is the origin. So I will directly give you the value. It's of course not accepted, but roughly it is around 70 kilometers per second per megaparsec. Megaparsec is just a unit of distance. You can go back and look at it later. But megaparsec is the unit that we use to express the distances to galaxies. All right. What this tells me is that if a galaxy, let's say, is at a distance of 1 megaparsec, then it is moving away or towards us at a speed of 70 kilometers per second. That's basically what the Hubble's constant implies. So if I have any galaxy at a distance of exactly 1 megaparsec, then it's either coming towards us or going away from us at a speed of 70 kilometers per second approximately. And how do you determine if it's coming away or towards? Is you measure the redshift of it. So the greater the redshift, so now we will come to this factor. How do you determine how?
Vikrant, it's slightly lagging. I think you can turn off your video.
Okay. Is my audio fine?
Yeah, there was just little bit of breaking. It's okay now.
It's fine now. Okay.
Hello.
Yeah. Hello.
I just have a question. I mean, as far as I know, the universe is like, the expansion of the universe is kind of accelerating, right? So
Right.
does that mean that 70 kilometers per second is going to keep changing?
Yeah, that's what the debate is all about. So the reason there's a debate going on about the value of Hubble's constant is we're still not able to figure out if this particular value changes with time. We don't know if this is going to stay 70 kilometers per second like for infinite amount of time, or is it going to change after a few million or a billion years. We're still not able to determine that out, or at least I haven't found anything that tells that. But yes, some people would say this is 67, some would say this is 72, some would say this is 69, and so on. But on an average, you can take it to be 70. It's fine. And when you do that, so the time is equal to 1 over h, that is 1 over 70 kilometers per second per megaparsec. You will find the age of the universe to be approximately 13.81 billion years. The accuracy of this depends on the accuracy of your Hubble's constant, but this is approximately how you find out the age of the universe. Any doubts so far? All right, I'm assuming there's none. So we will now move on to another topic where we deal with matter density of the universe. Right. Just give me 1 second. This COVID infection got my throat, so I just need to keep drinking water in between. All right. So now let's look at matter density of the universe. Now, what this basically means, you know what density is. It's just, uh, you know, density is equal to mass by volume. Very simple to understand. But what exactly is mass? What exactly is the volume? What is the volume that we're talking about? So here, this implies that we're talking about the mass of the entire universe divided by the volume of the entire universe. Pardon my handwriting, but this is not something you need to be noting down. Uh, so yes, and how do you determine this is from your observation. So what you do here is you calculate the distances to let's say a cluster of galaxies. You make a lot of observations of that, and once you are satisfied enough with the level of accuracy, what you can do is find out the intergalactic distances. So in a cluster, you have several galaxies. So what you can do is you can figure out the distances to each galaxy, and then using that, you can find out the volume of that particular cluster that you're seeing, and you can estimate a mass. I will not be getting into all of that. But with that, you can figure out the density of the entire universe. And what they found, what the calculations tell us is lambda, let's say theoretical, is around 10 power minus 27 kilograms per meter cubed, which means in 1 meter cube, there's around 10 to the minus 27 kg of mass there. And that includes your all stuff like, stars and all of those materials. But what they found, so the density that was observed, oh, in other terms, if you divide this by the mass of a proton, kg per meter cube, the mass of a proton is 1.67 into 10 to the minus 27 kg. This will give you the density of the universe, expected density of the universe, to be approximately 6 protons per meter cube, in every cube of 1 meter length. Right? This is what is supposed to be there out in the universe. But then when they observed it, they only found 1 proton per meter cube, which is approximately 20% of lambda theoretical.
Is this where the dark matter theory comes in?
Exactly, absolutely. So here, what they realized that this 20% is only from the luminous stuff that they can figure out, but almost like 95. That all the teams working on the dark matter stuff and also on the white dwarf and pulsars, I'm pretty sure that this is one of the basics where you started out from. So what they observed is only 1 proton per meter cube, which when you extrapolate tells you that only 5% is the let's say observable stuff, which includes your stars, galaxies, intergalactic dust, intergalactic matter, gases, radiation, all of that.
Um,
95%.
why didn't you talk about neutrons and other particles which have mass?
You could. Neutron mass and the proton mass are pretty same, so it doesn't matter what you take. This is just a rough, like a general stuff way of saying that this is sort of a thing. So this also means that there is around 6 H plus atoms in every meter cube. It's just a figurative way of, because if I tell you that if some random non-science person that the density of the universe is 10 to the minus 27 kilograms per meter cube, he's gonna be like 10 power minus 27. What, I can't figure that number out. So then I tell him that there is 6 protons, you know, something like that. It's just a simpler way of putting it that way. But you can pick any particle that you want. You can also put the mass of carbon here, and then you can tell ki there are so many carbons for every meter cube, or stuff like that. So yeah, what they found out is that only 5% of the stuff is observable, and that is why you're getting this particular density, and 95% accounts for your dark matter and dark energy, something that is like an area of active research. Research. This is something that you guys can always pick up, because I'm not going to get into dark matter and dark energy right now, because what we're going to be talking next is what happens to the future of the universe, and why does this particular density thing matter to us. That's what I'm going to be talking about, and how exactly do we get this 10 power minus 27, like what's the math behind getting that 10 to the minus 27. And also the reason I picked this particular topic to tell you how and why we got the 10 power minus 27 is because one, this was a astrophysics technical sort of an astrophysics course, so you guys need to be exposed to how you come up with uh, values that the scientists say. Why should you believe if I tell you that the density of the universe should be 6 protons per meter cube? This is one step of the entire scientific thinking and the process of science, right? You need to question everything that one tells you. I mean, not like doubts and all, but yeah, I hope you get what I mean. So what we'll do now is we will
Uh, I
derive.
have I have one question.
Yeah, please.
So in the previous slide, the t is equals to the 13.8 billion years. That is the age of the universe, right?
Yeah,
First,
well done.
yeah. So recently we read an article saying that they found some star which was 17.5 billion years. How was that possible? Like how did they calculate that particular thing?
Okay, so that I'm not so sure about it, but I guess what they do is, again, they figure out the spectroscopy of that particular star, and then they just calculate it in a similar process. But what could have happened is there might have been a error in measurement of the light, or some other factor that might have, you know, occurred in between, which might have delayed the light even more. So yeah, but the process is more or less the same, like I mentioned. But this is more or less that I am aware of. This is one of the ways they try to age stuff.
Or could it be that the star which we found, the old star, travel into our observable universe from outside what we can't observe?
Maybe I can't exactly
Yeah,
say,
we can.
give you like a fixed
Can
answer,
I
but
comment with that question? See, the recent
sure, sure.
this two black hole mergers recently also. So they were much, see, they were some so many billion light years. So probably, if I had the question, it is regarding the distance, not the time. The that star was how long, how far it was, and so that's the point. So when we say billion light years, so distance is a different thing than time. Am I okay?
Yeah,
So in fact, the last two black hole mergers were recorded, much more. I think 17 billion light years. Away. So that is much more. So the this is a unit of distance.
But here, sir, here the point is that you have light years actually light years is how far distance does light cover in 1 year, right? इसीलिए you have when you although a light year is a distance,
See,
it
to answer
means
your question,
like so many
Guys,
billion
to
guys,
light
answer,
years,
yeah, to
it
answer
took
your
so many
questions,
years for light
listen,
to
can
travel
we
from there to
keep this
here.
for later, please?
to answer your question, the universe diameter is 92 billion light years. So try to understand. So it has nothing to do with the time. The observable diameter of the universe is 92. So you get
All
that
right,
right.
can we come back to this later,
Yeah,
because we
yeah.
still
Sorry,
have a lot to cover.
sorry.
Yeah, that's okay. That's okay. It is definitely an interesting conversation, but I'm afraid there's also a time constraint here. So let's just move on, and we'll again come back to it. All right. Okay, fine. So we will now move on to figure out why the density, that the theoretical value is 10 power minus 27. And what we're going to do for that is we're going to cheat, and we're going to derive something called the Friedman equation. This was derived by Alexander Friedman way back. I don't even remember the year, somewhere in 1900s or so. But I will get into a derivation. Now, this is not so mathematical. It's just, multiplying stuff and all of that. All you need to know is the expression for potential energy and the expression for kinetic energy, which is just kinetic energy is half mv squared, and gravitational potential energy is gmm by r. That's the only thing you need to know. The rest, I will tell you how we go about it. So what we do is we make a lot of assumptions. First of all, we assume that the universe is spherical. We assume that, for the sake of calculation. So that means that I can put a circle here, and let's say that I am at this point of the universe at some distance r. All right. Now, what we'll do is we will consider the universe to be expanding. The universe is expanding. All right. So what that means is I will still be stuck on the surface of the universe, but what will happen is, let me just erase all of this. When after some time t, the universe would have been this big, this dotted circle, and now I would be over here, right? So what I'll do is I need some method of telling where I am, right? So for that I'll pick a coordinate system. Pick coordinate coordinates such that they move with you. All right. So when I was here, let me put that in red. So when I was here, let's say my coordinates was, let's say, x, right? From it doesn't matter from where, but my respective coordinate was x. Now what I want is when I am at this position here, I still want it to be x. Why? Because I'm not changing my position here. It's the universe that is expanding. I am not moving anywhere, right? What is changing, however, is my distance from the apparent center of the universe, because I assumed that the universe was spherical, right? So this is an apparent center. So I'll put this distance as r vector. All right, this is purely based on assumptions. So now I am picking a coordinate system such that they move with me. Such a coordinate system, by the way, technical jargon, are called co-moving coordinates, because they literally move with you. So co-moving coordinates. All right. So now if I tell that the universe expands or scales, scaling and increasing in size more or less mean the same. Universe scales as a of t. So a is just some. This is some sort of a function that depends on time. So why do I put this as a function of time? Is because as time progresses, I am in the same position, but it is the universe that is sort of scaling up. It's sort of becoming big, right? So that is why I put this a of t, and this is naturally called the scale factor. Right? We need not get into the details of how we get the scale factor and stuff. Uh, so now I can put up my position as a function of my coordinate as a of t. So my x doesn't change. It is my position that is changing. So this is changing. How is it changing? With time, it's changing like this. So as time increases, my position from here would increase. So after some more time, I would be on a bigger sphere. I would probably be here, but my this x would still remain the same, but my r would have increased. It would have scaled up. It would have become double or triple or something like that. So that is what this expression tells me. So my position is a function of the scale factor. Okay, or if I drop the vector sign, it's just r equals ax. That's it. Very simple. Something that we've been learning in physics, like ever since you start studying physics, is the law of conservation of energy. This is something that you've been learning for years now. For the people in people above master's level, it's been more like what, 8-10 years, maybe even more. But this is something that will still hold good. So what it just tells you is that the total energy is the sum of the kinetic energy T uh, plus the potential energy V. So T here is kinetic energy, V here is the potential energy. All right. Now you are in a sphere here, and the only movement that you're having is because of the expansion of the universe itself. So your velocity is equal to the change in r by the change in time. R is your position and t is your time. To make it a little more fancier, to make it so this I'll make this interval even smaller. In that case, I would write it as dr4v or just r dot. This I'm sure you're familiar from Allen's talk when you were doing understanding stars. So this is my velocity. All right. So I know kinetic energy is half mv squared plus the potential energy. We know this expression from your 12th standard, 10th standard physics is just g m m over r. Now this, the small m is, let's say, your mass, and the capital M is the mass inside that sphere. This entire whatever is there, that is the capital M. But this would still remain constant, as you would see, because all that's happening is that the size is increasing, but you're not adding in an extra mass or you're not taking out any extra mass. So this M, capital M, is still a constant. All right. So we have E equals half M. My V was what? R dot. So I'm going to put half mr dot squared minus gmm over r. Any doubts so far? Because this will get a little mathematical, so I just want to make sure that you guys understand it pretty well.
How
This
come
R
minus gmm by r square?
No, you might have to go back to your 12th standard physics to figure out that F is equal to minus gmm by r squared. That is force. But your potential energy is just minus g. Potential is a scalar quantity. It is not a vector. Is that clear?
That is because it is attractive, no? Gravitational force.
Yeah, yeah. But it's fine even if you do not know that it's an attractive force. All you need to know is the expression. I'm fine with that. You can figure out the physics of it later. All right. So assuming that there's no more doubts, I will move on. Now I don't want this m and stuff. I just want an expression in terms of r. So what I'll do is I'll go back to my relation which says density is equal to mass over volume. So you see that I've put capital M. That means I'm referring here to the density of the entire universe. This implies density of the universe. All right. So since here is where my assumption that it is a sphere makes it easy for me. So what I need is I need m. So m is equal to rho v. Volume of a sphere is 4 by 3 pi r cubed. Very simple. R was the position, so I'm just putting that R here. So I will put this in here. So that just makes it E equals half mr dot squared minus g small m by r. And for capital M, I'm putting rho 4 by 3 pi r cubed. 1r goes off. So I have E equals half mr dot squared minus g small m by r rho 4 by 3 pi r square. Okay. So let's move ahead. Yeah,
You took an extra r.
did I?
Yeah, you cut the denominator R, but
Oh, I cut the cube thingy, but that's okay. I get it. It's fine. So you just need to make sure that this expression is correct. So this is gm over this r will be here. Or did I make that mistake here? Oh, okay. Thanks. I always end up making these stupid mistakes. Okay, so this will not be here then. Okay, so this is going to be gm 4 by 3 pi rho r square. Now I know that r is equal to ax. So if I differentiate this, r dot is going to be equal to a dot x. Why? Because my x was a constant. My x remained same throughout, but it is a that depends on time. X is not depending on time. Right? So r, this just means that dr by dt is equal to dA by dt into x. No, I hope there's no confusion here. So we'll put this up here. So that becomes E equals half m So instead of r dot, I'll put a dot x squared minus gm 4 by 3 pi rho. No difference in that. My r is just ax whole square. I'll just expand all of this. A dot square x square minus, rearrange this. That's 4 by 3 pi g rho a square x square. Now you see that there is an x square term here. Did I miss m? Yeah. There's an m and an m. So what I'm going to do is I will multiply throughout with, and this 1 by 2 also is bothering me. So what I'll do is I'll do 2 by m a dot squared x squared. Right? This is what I'm going to multiply throughout. So let's see what that gives me. Oh wait, sorry, I'll multiply with a squared, not a dot squared. Just multiply with a squared. I still want, this is the only place where I have a dot, so I don't want to lose on that. So I'll just put the dot here. So let's see what happens. So I am multiplying that throughout. M a squared x squared into e is equal to half m a dot squared x squared into 2 by m a squared x squared. Okay. 4 pi g by 3 rho m a squared x squared into 2 over m a squared x squared. So this entire thing cancels out. From here, I can cancel out the m's and the x squared. So now I am left with 2e over m a squared x squared equals, what's left here? So I'll put the square together, a dot by a whole square. It's still valid. Minus 4 into 2 is 8 by what is this, g by 3 and rho. So this is what I have. So let's get to a new page. We have 2e by m a squared x squared is equal to a dot by a whole squared minus 8 by g by 3 rho. I'll rearrange this a bit. I want this particular thing to be on one side and everything else on the other side. So when I rearrange this, I have a dot by a whole squared equals, I'll put this first, 8 by g by 3 rho plus, did I cancel anything? No, okay, fine. Plus 2e over m a squared x squared.
There is
Now
a
what I'll
minus.
do is I'll multiply.
There's a minus sign.
No, it'll be a plus. When I take this side, it's going to be a plus. Both are plus terms.
No, you. Okay. Yeah.
It's still fine. It's still valid.
Yeah.
I
Okay.
just checked it. What I'm doing here is I'm multiplying and dividing by c squared, which is the speed of light. Only because this is like a lot of things that I don't want. I'm not dealing with the coordinate directly. I'm not dealing with the mass directly. All I need is the a term. So I'm going to put everything into one particular constant. So I will put this a dot by a whole squared equals 8 pi g over 3 rho. Now I'm going to explain what I'm doing here. K c squared over a squared. I'll tell you how that comes in. But before that, I'd like to put a box on this. And here where k equals, let's see, minus 2e by m c squared x squared. Is that correct? Yeah. All right. Now this is our Friedman equation. Congratulations to everyone who were writing it. You just derived the Friedman equation. Cheating, but why cheating? I'll tell you in the second part. This is the Friedman equation, and the reason I put it this way is because I just didn't want a lot of technical terms around here. Now, this is what helps us figure out what the density of the universe is and what the shape of the universe is. So how density is, because I have a density term here. So I can manipulate that, and I can figure out what the density of the universe is. And how shape is because of this k here. So k is just a fact. It's just a parameter, or you can just say a constant. Uh, and what? Let me just say constant. Let me say this is the shape parameter because it helps us determine what the shape is. And rho is the density of the universe. All right. Now, I'm not gonna tell you why, but the Hubble's constant is defined also like this. A dot by A can also be written as H, which is the Hubble's constant.
Can I ask a question before we continue?
Yep, yeah, go ahead.
What is this A dot R dot? I unfortunately didn't attend the other lecture which you mentioned before starting this.
All right. So, very briefly, A dot just implies that you're differentiating A with respect to time. R dot just implies that you're differentiating R with respect to time, nothing else. It's just a time derivative. It just tells you how that particular A thingy is changing with time. That's all.
What do you say?
Therefore, you are trying to say, in other words, delta A by delta T.
Yeah, yeah. Delta A by delta T, that is still like a large interval. Delta we use when the consecutive things that you're taking are too big. This is just the calculus way of putting it, but yes, delta A by delta T is your A dot. You can put it that way, and this would of course then be delta R by delta T.
What do you say?
Anything else? Sorry.
What do you say?
Okay, so A will go all the way back. I defined it here. A is the scale factor which tells me how the universe would behave, basically in terms of its size or something. It's just some sort of a constant that you need not directly worry about. All right. Um, Now I remember that in the page, I remember that during Alan's talk, someone asked about the relation between the cosmological constant and the Hubble's constant. Um, so if that person is here, this part is for you. This part answers your question. So we have the Friedman. I'm going to rewrite since my A dot by A was H. I'm going to rewrite the Friedman equation like this: 8 by G by 3 rho minus kc squared by a squared. All right. Now, there is a lot of mathematics that lies behind what I'm going to tell you next, but I will skip all of that because that will make it very complicated for most of you. What I will tell you is what this implies. All right. So, what I'll be telling you is how uh, the variation in these things tells us what it is. Why it tells us that is something that you might want to look up if you're interested. Otherwise, you'll just have to take my word for it. So we will get into that. So there's three scenarios. So there's like this k factor here. C square and a square are still some sort of constant that I need not worry about. So first I'll put, okay, let's say case one, I'll put k equal to 0. Then this equation becomes h squared equals 8 by g by 3 rho. I will rearrange this. Rho equals 3h squared over 8 by g. G is your Newton's gravitational constant, 6.67 times 10 to the minus 11. So now, if you take the value of h to be around 70 kilometers per second per parsec, like we defined Hubble's law, you will find that this is approximately, like I told you before, 10 to the minus 27 kg per meter cube. And this is something we call the critical density. So this is why I told you that the density of the universe is 10 to the minus 27, and now you have a proof for it. This is something that all physicists and mathematicians like alike, is that no matter what you say, you need to prove your statement, right? You need to have evidences for it. And I have just given you evidence for telling that the density of the universe should be this particular 10 to the minus 27. When I tell you that k equal to 0, that implies, with a lot of underlying mathematics, that the universe is flat everywhere. Now, what we mean by the shape of the universe is something that requires a lot of thought. But what you can assume it to be is if you just take like a plane, it's not straight, but I hope it will do. This is your entire universe and it expands in all directions equally. And so if you find out, if you try to calculate the angles of a triangle here, A, B, C, you will find that A plus B plus C equals 180 degree. This is what we mean by a flat universe. And here these points can be, let's say, some galaxy here, some galaxy here, some galaxy here, or some supercluster, some supercluster, some supercluster, something like that. And this is how you determine if the shape of the universe is flat. And how do you say it's flat and not something else is what we'll look into next. So in part 2, what I'll, okay, before I go to part 2, I'll define something, some easier thing. Since I'm going to be dealing with densities here, I will define a factor called omega as rho by rho c. Rho c is this value, which is this 3h square by 8 pi g. This is called the density parameter, only because you are writing it and you're just mentioning about densities here. So in that case, in for case 1, when your k equal to 0, omega is equal to 1. Why? Because your density is equal to the critical density. And this is the characteristic of a flat universe. I'll come to the cosmological constant a little later. That was one of Einstein's thing. So now let's just quickly look at case 2. If my k value was greater than 0, so I have h squared equals 8 pi g minus k c squared a squared. All right, so my case 2, if k is greater than 0, which means it's all the positive values, then my this particular, so if k is greater than 0, then eventually this part will become greater than this, which means this entire thing would go negative. Is that clear? If the k keeps, if I have like, let's say 5 minus k 7, if the k is greater than 0, then there will come a time when if I let's say take k equal to 10, which is much greater than 0, then 5 minus 10 into 7, 5 minus 70, which is minus 65. So you see that it ended up being negative. So if k is greater than 0, your density of the universe would end up being greater than the critical density. Because of the negative term, you take it on the other side. And your density of the universe would end up being greater than the critical density. And then what would happen is, if the density is greater, that means that there is a lot of stuff present in the universe, which means that there is a lot of gravitational interaction. Implies the universe will collapse. This is what we call the big crunch. Why? Because it's just gonna, after some amount of time, it's gonna come all the way down just to collapse in and itself, all because of gravity. And why do you have so much gravity? Is because you have a lot of stuff in the universe, and this is what k greater than 0 determines. All right. Next, we look at the third and the
Just a
final.
second. How do you define the equation if the whole right-hand side becomes negative? I mean, h squared, on the left-hand side, we have a square term, right? Does it have to
H
do with
squared on the
imaginary
right
numbers
side,
now?
just make sure that your h value is positive. It doesn't apply to the entire equation. Now here I have just a k. I do not have a k squared. K
No,
squared.
no, no. I'm saying if k is greater than zero,
Uh-huh.
if it is sufficiently big enough, then the whole right hand side can be a negative term, right?
Exactly what I said,
Yeah.
which is
Then
what I
then
mentioned here.
then how do we equate the equation? Then we would require to go to the imaginary numbers, right?
See, h here is a constant, so you're not solving a quadratic equation. K is a linear term. There's no h is a constant, c is a constant, and your a is also somewhat of a constant. All right, at least for these purposes that you're asking about. So then you do not worry about getting imaginary numbers, but yes, there is a possibility of that, but I will not be getting into that. It would get complex for a lot of people here, so I'm just going to skip that part. But you can look it up. It deals with the radius of the observable universe, and that's something you might want to look up. So I'll move on if you don't mind.
Okay, sure, sure.
Yeah. So if k is less than 0, then it's the obvious case where the density is less than the critical density, which means there is very little stuff, which implies there is not much gravity, which implies the universe will expand forever. All right. Now you will realize that there are two cases here. In case one, it was flat. Oh, by the way, this sort of a universe is called spherical. The shape of the universe will be spherical. Why? Because you have a circle. So if you're starting at this point and you eventually keep moving, you reach a maximum and then you start falling back again. So this is like your end
Excuse me,
point.
Vikrant.
Yeah.
I have a question. Yeah, k equals zero. Flat universe. Does it means universe will neither expand nor contract?
No, it will expand. I'm coming to that. I'm coming to that.
Yeah.
That's exactly what I wanted to tell you about.
Yeah.
This is called a spherical type of universe, and this is called a hyperbolic. Right? Yeah. This is called a hyperbolic universe. A hyperbola is a little difficult to draw, but try to find. It's like your fingers are related, so it's gonna be like this, and something like this, a saddle sort of a thing. So in that case, uh, it would, if you had two ants going in a straight line, then they eventually end up going away from each other. Whereas if you had two ants going here in a straight line, they'd eventually come and meet. Whereas in a flat space, if you had two ants going in a straight line, going in straight lines, they'd remain parallel forever. That's how you could imagine the spherical universes. So coming to this, it's flat, is spherical. 3, it's hyperbolic. Okay, all these deals with the geometry, and how we come to the conclusion that it is spherical or hyperbolic has to do with a lot of math behind. I'm not going to get into that. But then this is what we called a closed universe for the obvious reasons, because it starts here and it ends up closing itself. So everything is contained inside this particular sphere. Now this is one sort of an open thing, because it's you don't see any boundaries, right? There's nothing stopping it. And even this is like it. So even this and all of these shapes and stuff is very difficult for you to imagine. You can just look at it in terms of a simple graph. Make it big. My drawing skills are very bad, which is something what every teacher would say. But I'll try my level best to make sure this comes out right. So on the x-axis, I'll have time going this way. And on the y-axis, I'll measure the expansion of the universe. So in other terms, I will be looking at the scale factor, A. So this will tell me, this is like a factor that will tell me how much the universe is expanded or how big the universe is. All right. Now there's three cases. Just a moment. All right. Now there's three cases. So let's say we're starting out at the origin. Let's say this is the Big Bang. Uh, and now we are somewhat over here. Okay, let's say this is the present time. Now this is where we figured out this Friedman equation, and then now we figure out that there could be three possible shapes. So, but what is the future? I mean, what could be the possible cases? We don't know. We'll just have to sit and observe. But what you could figure out is how it's going to end. So you could represent all that we did in the last three slides graphically. So if it was supposed to be a spherical universe, then this is going to approach a maximum value, and then it's going to fall down. So after some amount of time, this is your big crunch. Now the remaining two are open universes. So what we'll do for them is one of them is flat. So we come all the way like this, and we just keep on going like that. And the other one, so this is for flat, and this is spherical or closed. This is flat or open. And the other possibility is from here we might keep going on and on. So the thing with the this is what hyperbolic, and this is also open. So the thing with the hyperbolic thing is they are what we call asymptotes, which means they would appear to reach a certain value, but they would never quite reach. They take an infinite amount of time to reach that particular value, and that's what hyperbola is somewhat all about. So if you remember your let's say 12th standard or 10th 11th standard stuff, a regular graph of a hyperbola was always showed to you like this. And you have one curve like this, and you have one curve like this is they would be approaching some value over here, some minus y and some plus y. So that's exactly what this means here, that it's going to be reaching after an infinite amount of time. It's going to slow down, but it's never going to stop expanding. That's what this basically means. So as time progresses, even here it's great, but after some time it's going to slow down. What this means is it's going to keep accelerating forever, and what this spherical one means, it's going to accelerate for some, some maximum amount of time t naught, and then it's going to start decelerating, and it's going to come all together, and you're going to have a big crunch. And this ends my section on cosmology. So this is how we determine the shape of the universe, and this is how we figure out what might happen to our universe. And the only way we can figure it out is by observing. What observations already tell us, you know, based on what they've done already, is that A plus B plus C is very close to 180 degrees, which means that the universe is, or universe apparently is flat. But then we cannot conclusively tell that. Why? Because if you go stand up, go on your terrace and look outside, look far away, it will look flat. But does that mean the Earth is flat? No, it's just that the area you're observing is very less. So it is possible that uh, we're looking at a smaller section of the universe, whereas in reality it could even be hyperbolic or it could even be spherical. We never know. But so far, we've found evidences that tell us that the universe apparently is flat everywhere, which means we might be heading towards a flat, open universe. And that concludes my talk on cosmology.
Yeah, excuse me, Vikrant. Yeah.
Yeah, go ahead.
Yeah, are these the only three cases possible?
Yeah, I mean, if you look at the equation here, if you see this part, there's only one thing that sort of can change in the entire thing, right? So just write that fresh. You have h squared equals 8 pi g by 3 rho minus k c
Yeah. With
squared
this
by
equation,
a by.
yeah, only three equations possible. But I'm asking about the according to other theory and hypothesis, is there any possibility of the shape of universe could be something else other than these three?
Possible, but I haven't read about it. But these are the three most probable possibilities, because I think you also need to consider. I mean, they also did consider the energy levels and all, and a lot of stuff back there. But yeah, and these, by the way, were derived the Friedman equation that I just derived in a cheating manner were derived originally from Einstein's field equation, which some of you might have seen in the start. Minus.
Does that also have the universal gravitational constant?
The Einstein field equation?
Right.
Yes, it does. 8 pi
Okay.
g by c power 4 t. You can ignore all of this.
I've also heard that there is some debate that the gravitational constant might not be constant. So,
Yeah,
um,
it's all to do with the same reason that the Hubble's constant might not be a constant. The same
okay.
arguments apply there.
You missed an
Okay.
R in the Einstein field equation.
And what if I go crazy
Hold on.
and what if I try to input something imaginary for as a value of k? Not positive, not negative, not zero, something imaginary.
Then you'll probably have to work out and see what answers that give you.
Is
I
there
haven't done it, so yeah.
is there like any possibilities of is like sorry, is there any experimental evidence for this? How
For
do they calculate this all, you know?
for this shapes and all.
Yeah, the shapes and the equations. Do they satisfy in
Okay,
the real life?
so the equations are derived from the Einstein field equations, and how the Einstein field equations are derived, that's another long story. But you can be sure that the EFE, the field equations, are correct, which means that these also would be correct until someone, sort of uses this to prove that it is wrong, proof by contradiction.
No, I mean the geometry.
The
How do they
geometry
calculate?
deals with a lot of just one moment. Let me tell you what and all it has. I did make a note of it, but then I didn't want to mention it because it does get quite complicated. So for that, you'd have to get into general relativity because that's how you define the models of the universe. Where did I put that?
Use the FRW metric, right?
Yeah, that is the actual
The
way of
Friedman
deriving these
limit
Friedman
rose.
equation.
Yeah.
Yeah,
You
that's
use
the
that
actual
metric.
way of deriving the Friedman equation. This was like a cheating,
And it actually comes out
but
very
it's still
naturally
valid.
there. It comes out very naturally.
Yep, but you can understand why I didn't go through that.
Yeah, of course. No, I've done derivation, so yeah.
Right. I remember that cosmological constant thing. Just
When
wanted
it
to.
comes to evidence, I think if it really was a curved space, we should have seen certain distortion in light. But we have a lot of evidence for why it is a flat universe rather than why it is.
Yep.
Yeah.
That's what the evidences suggest. So, like I said, we'll just have to wait and watch to see what happens, to see if we find any contradicting proof to tell us that the universe is not flat. So yeah, this is observation, and that's where the research lies, right? That's what you are to do. Okay, a quick 5 minute thing about the cosmological constant. So this was introduced by Einstein himself because he did not want to believe the idea of a static universe, even though Hubble and all showed him that the universe is expanding. So he introduced this particular constant to make sure that the universe remained constant and it did not expand throughout. And why is it this? Why is it plus 1/3 lambda c squared? You'd have to go through the entire rigorous derivation of the Friedman equation, but this is how the actual Friedman equation would look if the cosmological constant were to be included. Now, for a flat universe, because that is the simplest case that we can take without any mess, k equal to 0. So this just reduces to h equals 8 pi g by 3 rho plus 1/3 lambda c squared. Now, you remember I defined this omega as rho by rho c, where rho c was 3h squared over 8 pi g. Now, you saw that this was somewhere around 10 to the minus 27. So what I'm going to do is I'm just going to ignore this part. I'm just going to set it to 0 because it is anyway a small value. Then I can just write this as h squared is approximately 1/3 lambda c squared. Let's put c squared in relativity. Okay, let me cut that. In relativity, whenever you're considering, you don't you're just very lazy to write C everywhere, so you just put C equal to 1. All right, so you just ignore that. So you have this relation where lambda is approximately 3h squared. So for the, I don't exactly remember who asked the relation between the cosmological constant and the Hubble's constant, but this is an approximate relation between them. And you can figure out that this is actually a constant value, and you can calculate it putting the h value.
Is c here the speed of light?
So yeah, c is the speed of light. C is.
Then how can you equate it equal to 1?
It's just a system. It's just a choice of coordinates that you'll understand when you do special relativity. It's just a choice of coordinates.
Okay.
Because in special relativity, everywhere you deal with the speed of light, you just get very lazy to keep writing it again and again and again. So you just put that equal to 1 and you're done. Everywhere you have c, it just becomes 1. So it's fine.
Is it similar to using c as one unit of velocity?
Yes.
I mean, maybe
Time.
one.
Define time. You use t equals the time or distance. How you define 1 meter?
Yeah, I was talking like the way we define 1 meter per second. In the same way, in different unit, defining c as
Yeah,
one
so in
something.
relativity, what you do
Is
is you
it the same
define a
thing?
coordinate system where each unit of distance is like the distance traveled by light in 1 second. So this is like c.
Oh, okay.
Something like that. It's just a choice of coordinates to make life simpler. Einstein did a lot of these cheating stuff, so it does make life simpler. But yeah, this concludes the part 1 of my talk. Now I understand that I've taken a lot of time. What is the time? 6:30. All right, Sitara, what do you say? Should I continue ahead with the math of GR, or
What else do you
should I
have
talk
left,
about?
Vikram?
Still have the second part of the talk. That includes.
Okay, yeah, that's why I felt we should split it into 2 talks actually.
Yeah. So, do you want to split it and put it in another date or another time? I'm fine with that. But if everyone's okay with it, then let us know.
Yeah, we do have some time this weekend, I think. So, or if Thursday is okay for you, we can continue this on Thursday.
Yeah, sure. But
Okay.
as I understand it, Aman might use a little math, right?
Yeah, Aman will be going into a bit of math of gravitational waves, but also fairly from a pedagogical view, he has to cover a lot of fundamentals. So
Fine then.
yeah, this might actually be necessary, part 2. But I think it will be a good continuation to Aman's talk. So let's do it on Thursday.
Sure, fine. No problem.
Okay. Yeah. Aman will give a very wide perspective about gravitational waves, detection techniques, and so on. Then you can talk about this, and immediately Saturday, I think we have Kanchan Soni's talk about detection techniques in specific. So yeah, that will be good.
Cool. So I'll keep like one session for GR alone then.
Yeah, Thursday, just one session for GR.
Sure.
Okay.
Can you give me the page number 4?
Page 4. Yeah. Is this what you wanted?
No, just next.
So the next one, that's page 5.
Yes. Thank you. Thank you.
Anything that I can clear up to?
No. Thank you.
Okay.
When was the shape, like Friedman equations and the shape of hyperbola, parabola, and all that determined, like found out?
Friedman equation and all, I think, were derived somewhere in the after 1915 for sure. Let me just figure out the date. Just give me a moment. Should be somewhere here. These dates are something that I don't usually like remembering because I just never liked them personally. There's just a lot of information. But somewhere, yeah, I think it should be somewhere in the 1920s after Hubble also discovered his expansion of the universe.
Okay.
So I think in the late 1920s.
I think you mentioned the date 1929.
Yeah, so it has to be after that because yeah. But yeah, you can assume it to be somewhere between 1920 and 1940. There was a
Okay.
lot of work going on in GR and stuff like that. So yeah, the late 1920s, 1930s ish. Any other questions?
Yeah, one. See,
Yeah, please.
we are told that near the black hole, the space is extremely curved. So that is negatively curved or positively curved? I mean, hyperbola or spherical?
I'm sorry, your voice sort of broke in
He's
Yeah,
between.
asking the
yeah.
shape of the universe.
I'll repeat myself. So, you see, we are told that near the black holes, the space is extremely curved. So, this
Mm-hmm.
curvature is negative or positive?
Oh, okay. That's a fun question to which I do not have an answer right now. But I think I'll probably get back to you if that's okay.
That will be nice. You have come back with this equivalence of cosmological and this one, Hubble constant. So please come back. Thank you.
Sure, sure, sure. Yeah,
Or we'll come back to you.
definitely. Anything's fine. But I'll try my best to let you know by tonight itself.
And one more thing, Arti was asking, the likelihood of universe being flat or spherical or this. You see, if you see the fractal process across the universe, everything is spherical, from small to big, across scales. It is all spherical. Do you have any object which is flat or negatively curved in the universe?
Yeah, fun questions you ask. Any object that is flat. I don't think it would exist because sphere happens to be the one with the least energy. So even if you did have a flat, let's say a flat planet, then it would eventually collapse to form a sphere. And negative curvature would imply an imaginary radius, and that is just a mathematical object. So I don't think anything with negative curvature would exist out there. And flat, even if it did, I don't think it'll be there for long.
Yeah,
Vikrant,
excuse me, Vikrant. Yeah.
Thank you.
Hello.
Yeah.
actually, that curvature, no, if we choose black hole to be the center, then the curvature is positive. I learned from maths and curvature
Oh, okay.
topic also.
Nice, nice. Thanks for letting me know about that.
Excuse me.
Well,
Yeah.
I'll probably
Vikrant.
read more about it. Yeah, please go ahead.
Yeah, I have a question. Like you said that sphere would have minimum energy, which leads to maximum stabilization, right?
Mm-hmm.
Yeah, but since we think that universe is accelerating, so does it mean that whole universe is in equilibrium state? Because many of the cosmological
No,
objects are spherical,
you
though.
need not get confused with the shape of a planet with the shape of the universe. Right? Those are two completely different things. What you mean by the shape of the universe is how 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 do I put
How the
this in simple?
coordinate system is shaped, basically.
Yeah, sort of.
You
Sort of.
could say.
How would light behave if it was
Yeah.
traveling far distances? That's what you mean by the shape of the universe, and it doesn't literally mean that the universe is a sphere. Right? It doesn't mean that we are on a on we're like on the surface of a sphere or inside a sphere. It doesn't mean like that in that sense.
Okay, okay.
Yeah. It's
Thank you.
like your ball is round, but the house you live in is somewhat square. It's
Yeah,
that
yeah.
sort of a comparison. So you cannot actually relate those two.
I have a question. What about 3D and 2D? When you say flat, you usually say of a 2D plane, right? Right.
I represented it in 2D, but when I say flat, it can also imply a cubical sort of a structure. But there's also the time
Cube or
limit that you
cuboid,
need to
basically.
consider. You could say cuboid, like if you just want to imagine, but there's also time that you need to consider because it's not just space that we're talking about. So coming to that, there is this statement called the cosmological principle. I just remembered this, which says that the universe is let me put it in like very simple terms, is same, as in it looks same to everyone from a very far distance. This is something called be called isotropic, and this principle is one of the assumptions. I mean, is one of the reasons why I assumed that the universe was spherical while deriving the Friedman equation. Why the universe was a sphere. This is something that you guys might want to look at because it has some sort of a philosophical approach to it. Like, if you look at your sky right now, it would be different from the sky that I am seeing right now. But then if it's an analogy, but if I were to go very far away from Earth, then all of the skies would eventually look same to me, something like that. So yeah, this is something that you might want to look at. I'm not sure if I answered your question though. I just sort of deviated in between.
Uh, we- I had a question.
Yeah, go ahead.
If universe is considered as flat and hypothetically assuming that it is like uniform throughout, how would abnormalities in the uniformity of the universe like cause distortion? Like for example, if a photon is moving by that abnormality, how would that affect it hypothetically? I don't know if
Right. So
it's
that is also one of the topics that is being done by studying the cosmic microwave background. Right. So you have, let's say, this is the entire background, very bad shape. But if we believe that inflation and all is true, so what we are doing here is we tell that the inflation happened and that the universe is isotropic. We're telling both these. Now, what does isotropic mean? It means that any section that you see here would be equal and the same as any section over here. But you see the distance between them is like some billion light years. So how could this possibly be the case? Right? So that's where inflation comes in and tells कि possibly when the universe started out as a single thing, uh, these sections of the sky, all the sections of the sky were in turn the same. So in other terms, you could say that they were entangled, not exactly quantum entanglement. I don't know if it is quantum entanglement, but as far as I could remember, this is one of the theories that I happened to read, that way back before even during the time of Big Bang, everything was the same, which is why any change that would happen here, change one, would also reflect over here, which change is proportional to one, something like that. So that is why you could say that uh, the portion of this sky and portion of this sky is the same, but something like that. I hope I answered your question right.
Yeah, there is the homogeneity will also come now. Homogeneity and isotropy, they are
Yeah,
the
that is
two
the next
properties now.
part of the cosmic wave principle. I just didn't want to mention it. There's a lot of stuff here, but yeah.
Yeah.
Okay, I had another question.
Mm-hmm.
So when light is redshifted, right, the
Mm-hmm.
wavelength increases, obviously.
Right.
So, and we know that energy is h nu or hc by lambda. So you have a loss in energy. Where does that energy go?
Okay, so it's believed that that loss of energy goes into the expansion of the universe, but I'm not completely sure of what happens. So it is obvious, right? I mean, if you think about it, let me just probably draw it. So there is, let's say, a blue star here. Okay, and let me put us in green because we're a green planet, no longer, but okay. So now let's say that this does emit blue light. Green. Let's say that this emits blue light, and the distance is d. All right, so this is lambda blue. Now what happens is after it moves, let's say until the midpoint, um, starts here, but we end up moving farther away, right? So then your distance would be d plus delta d, whatever that distance is. So then what happens is this light cannot stop. There's nothing to stop the light in between. So what will happen is this will spend its energy to make sure that it keeps moving forward. something of that sort. I'm not sure if that sort of helps you visualize it, but yeah. So this energy is lost because of this expansion delta T. If this wasn't there, if this was the case throughout, then we would get lambda b here and lambda b here. But if this is the case, then we get we had lambda b here, we have lambda red here, and by the time we get it here, it's lambda maybe IR or microwave radios. And all of that energy, let's say if this was in gamma, then it is spending that energy to make sure that it keeps moving forward. You can think of it that way. So in other terms, that energy is lost in the expansion of the universe.
I mean, but wouldn't it keep moving forward anyway? Since a photon is massless, it's
Yeah,
stopping
it
it
would
which
keep
requires
moving.
more
It would.
energy. So, I
See,
mean,
it's like the universe is stopping the photon to make sure it doesn't reach us, but the photon is adamant on reaching us. It's like a fight between them. Something of that sort. But I might have to go back and read more on this.
but
Because
but
this
that,
is
that
something
that's going to happen only if the velocity at which it's moving away from us is greater than the speed of light, right?
not
I mean,
necessarily.
otherwise it's going to reach us eventually. I mean, it has to reach us.
Yeah, it will, but yeah, it depends on how far that particular thing is. So if let's say this particular star, this red star was like I don't know, 10 to the 13 billion years away. Yeah, put c equal to 1, or 13 billion light years away, then this would never reach us because it's greater than the age of the universe. I don't know if there is a star like that, but yeah, if there was something like that, then it would never reach us because by then the universe has expanded so much and the distance has increased so much that it would have probably gone too far radially. It won't get a chance to even detect it. It's gonna get, if it was this big here, it's gonna get smaller, 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 smaller. Probably might have come across something and died there, absorbed there, and you would never get a chance to see it. Even if there was nothing, it would just get smaller and smaller and smaller until it's almost invisible. But it's there.
So I wanted to ask a question related to academics. Can I ask?
Yeah, sure, go ahead.
Yeah, so this might be a stupid question, but I actually have interests in all the three subjects like cosmology, astrophysics, and observational astronomy.
Okay.
But I like everything, but I cannot filter it out. So, yeah, how can one filter it out?
Can I ask which grade are you in? I mean, what are
I'm
you
an
studying?
undergraduate, in second year undergraduate.
Second year undergrad. Okay, so it's fine if you're not able to figure out stuff, because there is. I wasn't able to figure out my field exactly, and I'm still not able to figure out what I want to do my master's thesis in because I'm interested in quantum field theory, in relativity, in this thing called quantum chromodynamics, quantum electrodynamics, and a lot of other stuff. So even I haven't been able to figure out what to do. So the best thing you could do, or at least what I have been doing so far, is read everything, pick up one particular thing from each of the three topics that you mentioned and study it extensively. And by that I mean learn the required mathematics of it, learn the physics of it, uh, try to get the stuff on your own. And by that I mean, go through several research papers and on your particular topic, and then you will eventually end up liking one topic more than the other, right? So like that you could filter out. It'll take a lot of time, but that's perhaps the only way that I could suggest. If others have any good ideas to filter out their fields of interest, then they could, and I invite them to share that with us.
No, you're right. Actually, like in-depth study is the only way to really decide if you like a particular subject. Surface study will not get you anywhere.
Yeah, so there I have
Okay.
some backing up my answer.
Okay, thank you.
All right.
I
Any other
doubt.
questions? Yeah, go ahead.
Like you said, like whereas light propagates from a long distance, it loses energy, and we have dark energy which is actually like expanding the universe. So in a particular place in space, if dark energy is like expanding it, there's a void created, and it actually fills the energy there. Like So the whole universe's energy is like, maintained constant. So if light is like losing its energy and dark energy is giving its energy, like whose account is all this energy going to?
That's a pretty good question, but I think if the law of conservation of energy is supposed to hold universally, then I think that would sort of balance each other out. Which is why I sort of said that the light loses its energy to the universe itself, to the expansion of the universe, whatever the reason be, dark energy, dark matter, or whatever that is. But I think that would be one of the supporting statements to say that the law of conservation of energy holds universally.
Okay, so I also wanted to ask a question related to the contraction of the universe. So, for example, hypothetically, let's assume that the universe is contracting. Okay, so that means that whatever the light is coming to us, it would be blue shifted, right?
Yeah.
Yeah. So, for example, if it was like really fast, then we would be receiving gamma rays. So who would be giving energy to that if it was possible?
Wouldn't it be carrying energy from the source itself? And now
I mean,
see, I mean, I get it. So if you're telling that if the emission, if the source was radio, wouldn't it gain energy because the universe is contracting? That's what you mean, right?
yeah, so you're saying that whatever the energy it took for the universe to contract is converted in the blue shift. Is that what you mean?
Yeah, that is one of the possibilities. In fact,
Okay.
you answered your own question
Okay.
without me even
Okay.
trying.
Okay.
Yeah.
Thank you.
Sure.
Inversely, did someone ask about where the energy goes when it gets redshifted? Like, doesn't it mean that the light has lost a bit of energy?
Exactly. So these are like the inverse statements.
Yeah, and I think related to this, there was a woman, a mathematician called Noether, Noether. So Noether's theorem is one of the most influential theorems in this particular domain. So not a lot of people study about her, but her work in physics was short but very profound. So I'll send some.
Noether's theorem was actually about symmetries. That symmetries lead to a conservation law, basically. That's the
Exactly.
Noether's
So
theorem.
that symmetry theorem directly says that it is allowed for light to go through these transformations without violating the conservation of energy.
Right.
So if you look at it from an objective point of view, it looks like there is a violation here, right? There is nothing happening, but the energy is
The
going
light is
somewhere.
getting, yeah.
Yeah. So her theorem basically gives the freedom of certain degrees in space, which because of those symmetries, saying that yes, this is not considered a violation of conservation of energy.
And if you could dig out and do like an extensive research on it, perhaps you might also be able to prove that this is a strong evidence for dark energy being the reason for expansion of the universe or something like that. Maybe find some sort of a reason. I don't know if research is done on it, but this seems like a very interesting topic to look at. So to all the dark matter people out there, this is a chance for you.
So I found an answer on the internet where somebody had asked the same question that I had, and I posted the answer here on the chat if you want to go through it.
Okay. Can I stop sharing now, or do you guys like want me to answer any other written?
Yeah, I think you can stop.
Alright, stop the sharing.
Can you, I think Aditya, can you put this on the Equinox lounge as well?
Yeah, please put it in the Equinox lounge.
Yeah, sure.
We'll
The
lose
screen
it.
chat goes off.
One second.
I hope you guys found the talk interesting, though.
It was quite.
Yes, we did.
Yeah, it was nice.
Excellent.
Thank you.
That was really good.
Really
Well put. Quite basic, but very well put.
I actually wanted to do the math part, but damn, time.
It would be. I would say it would be better if you go beyond the metric tensor as well, but take more time next time.
Beyond the metric tensor is just
metric tensor is like, it's like you almost reached GR. You haven't actually reached GR, but you're almost there.
Exactly.
Which is very nice if you can just go slightly beyond
it
that.
as the basic math of GR.
You could tell us like action principle and stuff, how it's derived from an action principle, the geodesic equation.
No, I think people would just run off.
But like that's the beauty of GR, to be honest. That's where it really starts, right?
But I will consider that. Let me see if I can go a little ahead in metric tensors and see till where I can come.
So Thursday it is then, right, Vikram?
Yeah, if everyone's fine with it, I do not have a problem.
Okay, while everyone is still here, I think my microphone is kind of bad. But tomorrow is Professor Makbul's talk. It's a lecture by Dr. Makbul. He's actually ex-team leader at ISRO, and currently he's in the University of Hyderabad as a principal scientist. So yeah, I request everyone to be there. First of all, show up. But also, it's going to be YouTube live, which means the Zoom call will be streamed to the public as well. So yeah, be there, ask some good questions. He's an extremely experienced man. He's had like 40, 50 years of experience in space technology and the related fields. So yeah, so just to let you guys know that it's going to be live streamed. And yeah, don't bunk the lecture. You get only limited opportunities with people like this.
And the timing will be?
Oh, we are going to have it in the afternoon tomorrow. So 3:30 p.m. we'll start. Yeah, it might be 1.5 hours.
So I think we can now conclude the session.
Okay. Yeah. Thank you so much, Vikrant. You explained it very eloquently. Thank you.
I'll have to Google that word. I don't know what it means.
Nice handwriting also. So send us the notes if you're able to convert to PDF.
Yeah, sure. I won't be sending this one. I have another set.
Okay. Yeah. Okay. Thank you, everyone. See you tomorrow.
Thank you.
Thank you.
Thank you.
Thank you.
Good night.
Thank you.
Thank you. Bye bye.
Welcome.
Thank you so much.
And also especially to note that Vikrant was not so well, but he still did a talk. So thank you for that.
Yeah, perhaps you should have mentioned that, but everyone is here.
Yeah, and 11 people, but it's okay.
I'm going to eat apple because an apple keeps it locked away.
I knew you wouldn't be able to finish both when you said 2 hours.
I know, right?
Yeah.
No, plus I thought it'd take only like 1 hour.
No, dude.
There were a lot of doubts in between. So
2 topics. Yeah, the doubts will take more than like 40 minutes. So yeah, you have to factor that in.
It's fine. In that case, then it's going to be like a full math session later.
Yeah, Thursday.
I had a talk with Aman and he was like, if I did this, it would have been a good precursor to his. But,
no, it will also be a good post cursor because I think he'll be like going into it and talking about all the different stuff. So after that, you can enter GR in a bit more detail.
I'm so tempted to send the derivation of the Riemann curvature tensor, but you guys can leave.
Yeah, we're just like hanging out. Also, we'll make some nice lectures. How good is your internet actually?
I don't know.
If your video quality was slightly better, it would have been nice. But since we want to record some of this.
What do you do with this face? Look at this.
That is nice. You look like a theoretical physicist properly. So.
Yeah, sure.
Most of them have it actually. I hate making Canva posters. It's not, you know what? Since you're the appointed, I don't know what you are, but whoever you are. Can you please find someone?
Hey
It's
Vikrant,
your job.
can you make a
Wait,
thank
I
you?
found someone. She's a friend from Mysore. And she might be interested to do the designing and the social media posting stuff if you're okay with it.
Vikrant, can you make a thank you poster for today's speaker?
Yeah, bro, sure. What do you want me to put? Who's the
Yeah,
speaker?
that's there on the Trello as a to-do. Da. I can't do it. I'm very lazy. Can you make?
Yeah, sure. What do I thank myself?
Yeah, just write few lines about how nice your lecture was. And put emojis.
Sure.
I'm sure
Why
it'll
is Jivan
be.
saying yes?
Yes.
Yes.
Uh, I think I want to take the day off.
Is there anything else after this for you guys?
Oh shit, yeah. I completely forgot.
We had that data driven
Coding with
economy.
pulsars. Oh no. Jivan.
Come, we have to prepare.
You're only teaching today, yaar. I'm taking off.
I'm also taking off.
No, I'll take off.
I
Tomorrow
still
you
have to
take off.
finish.
No, please.
I am so glad I'm not a coder. I mean, I did the course, but yeah.
Oh, come on. You have to teach derivations after derivations. We just have to be like, guys.
Type.
Yeah.
No, but still, that does take a lot of logic. So.
Yeah, can you tell me what you're using? Some tablet, is it? What is it?
Yeah, it's a Wacom one. WACOM.
Okay.
Yeah, it's a small one though.
Nice. How much does it cost?
3K-ish.
3K.
Yeah.
You bought it for your new tuition job?
No, I bought it because I was fancy. I wanted all the fancy teaching stuff. The tuition job thing, I got like, I don't know, 2-3 days back, which is postponed to next week, by the way.
I'll also buy a tablet. Actually, Vikrant, can you handle Pulsar's group today? You've done the course, I know. You went till cross matching. I know.
No, I'm not doing it. I might have to address my own T1A people. I don't know.
Arey yaar. Jivan, I'm leaving here. I'll meet you at 9:30. No, please finish off and then come. No. Come after that, okay? I'll be around after 9.
Me too. Bye.
Bye.
Okay then.
Let's mutually ditch each other.
Arey, I wanted to mute Jivan, dude. Shit.
Bye, Natasha. Thanks for joining
Bye,
our
Natasha.
party.
I've had to hear to a lot of nonsense the past 5-10 minutes.
Yeah.
Is she even there?
Hope you find it appealing that your teacher is now eating apples or whatever.
Is she even there? I don't know if she's there.
No, I don't know. Okay.
Join
Bye.
Discord, yeah. Chalo, bye.